So good afternoon. So we are starting a new talk in this series of industrial talks promoted by IEEE Sequencing Systems Society chapter Rio Grande do Sul, and also Sequencing Systems Society Region 9, as well the chapter of Calcium EDA in Brazil. So it's a pleasure to have here today Jesús Palomino Echartea from Intel Mexico. And the talk will also be shared with Jorge Hermosillo and Esdra Juarez. So thank you very much to all you to accept our invitation. So Jesus, I'm not going to tell all his CV here. You can see in the flyer that was distributed. And but Jesus is now the general manager of Intel's Guadalajara Design Center. So that has more than 1,100 engineers, and so they are doing a very nice work, as you are going to be able to see in his talk. So I give the floor to Jesus to start his presentation. Before that, I'm going to upload his slides that's here. So now, Jesus, you have the control to start your presentation. Thank you very much.
Thank you very much, Ricardo, and really happy to be here. So thank you everyone attending and welcome to this presentation. I'm going to talk about the Guadalajara Design Center. That when I talk about this, I generally use a term of a success story. And I believe it's a success story of the Latin American talent developing products and technologies that have a worldwide impact. So we will talk about what we do at the GDC, but we will also provide a couple of examples, one on the research area and the other on the development area, of how we are impacting Intel leadership with what we do here in Guadalajara, Mexico. So this is our campus. We're very proud of our campus because has shown that from the very beginning you can aspire high. And this campus was developed following the leadership in energy environmental design construction. So it is the first LEED Gold campus a few years ago in the region. Now there are more, but in every aspect we try to show a leadership kind of a message to our community and help precisely that community to advance. So this is a couple office buildings and one large lab building. We are part of an ecosystem. This is what we talk, what we call the Guadalajara Hightech ecosystem. All these companies are here, and we try to work together, as in any ecosystem, to advance each other, to support each other. So it is not only the industrial part, but also we have the academia part, government part, and other functions that are growing, like venture capital and so on. So this is the current high-tech ecosystem in the region, generating around 100,000 jobs. Like 70% of that related to manufacturing, but the area of development design is growing. So let me start with our key asset people. We are a little bit more than 1,000 engineers. 45% of them have a postgrad, either master or PhD. Then the other 45% bachelor, and we have 10% that includes interns and some technicians. And this is composed a majority of Mexican engineers, but we do have engineers from several countries in Latin America, as well as other countries. The domain areas are electronics, computer science, some mechanical, thermal, industrial engineering. Majority of the jobs here, I might say 95% of the jobs are technical. 20% of all our engineers are female engineers, women, and we want to grow that because we believe on that talent, on the innovation that they bring to any organization. So we have some initiatives towards supporting that. On technical leadership, we have a set of what we call technical leaders. This is some of our engineers that are recognized by the knowledge they have, the experience they have, the results they deliver, or kind of the forums and groups they drive. We have expertise in several areas. I will talk about research, silicon development, platform development, and so on. And on IP generation, that is one way to measure technical leadership, not the only one, but one. We have been contributing with the inventions, patent submissions, and some of the patents have been granted, mainly in the US, but also in other countries. As a reference, we're above the Intel average on patent generation per 1,000 employees, which is good. We still have a room to grow, but so far so good on not only leading products, but also developing intellectual property that helps in the leadership of Intel. So this is what we do in this site. We go from research to silicon development, platform development, then software development, as well as integration of a full system and validation. And we also have groups that do the customer support on our technologies and products to several companies. We will talk in the next slide on research, and Esdras will be talking a little bit more about that. But on silicon development, Jorge will talk on how we are developing some IPs for that will be integrated in the future computing platforms. But we also develop the full computing platform. Sometimes the first computer that is going to use the next generation of processors is designed in this campus, because we had to do a validation process with all that, basically integrate a full computer with a new chipset, a new CPU, software stack, and so on, and make sure that works properly. So that is one of the strengths of the site, where you need to understand not only the component, the CPU, the chipset, but the full platform or the full system, how everything works. So to accomplish that, we do electrical validation, making sure new interfaces perform properly when you change different type of parameters. Functional validation, that every function, every interaction works properly. Security validation, also looking at that our designs are robust. Compatibility validation, making sure that the platform works fine with the multiple external components, other type of memory, drivers, and so on. So that's what we do in this box that we call software system integration and validation. We also develop some applications that help us test the new instruction set or measure how they perform. On platform development is the full stack from architecture, logic design, mechanical design, thermal design, the full box, everything. We have the skills to develop all of that. Majority of what we do on all these boxes is related to the data-centric platforms. We do also some project related to the client platforms, that I mean the PC, the laptop, but the majority has to do with the data-centric. So multiple functions in an open environment, that is part of Intel culture, how we have an open environment where everyone grows with diverse talent, that we bring diversity as a value to our organization. Just sharing a little bit about research. This is some of the areas that the research team on this site does. We will talk just of one of them, but as you can see, there is a variety of things that might range from algorithms, from artificial intelligence to full SoC design, and so on. So we will not talk too much about all these things, but just to highlight that the research in Guadalajara includes multiple areas, multiple research topics, and so far so good in the way that the successful delivery of projects and successful generation of IP in the form of inventions or patents or concepts that eventually are tested in a prototype so that they could be included in future platforms and products. A key for us is to deliver value to Intel. but certainly another key aspect is to deliver value to our community. So in addition to the great work our engineers do, we have multiple community engagements through corporate social responsibilities where we help on multiple areas, no? On innovation, on the mentoring students, on helping the forest or parks in the region, helping schools and so on. We partner very well with academia. We have frequent conversations with more than 20 universities here. We have a robust internship program, deliver keynotes and so on, because the value of academia is really important for the success of this campus. So from day one, we have been engaged with academia. On industry, we partnered in different industry chambers also to how we work together to bring more value to this region. And I will talk more on the Innovations Lab Network, but that is another initiative where we're trying to set up innovation networks across Mexico. This is the current innovation labs that we have across Mexico, and we help basically to set it up to foster that mindset of innovation, get them all connected, and support them. No, but basically the innovation is driven by themselves. We just support them. All the IP is owned by that academia or that industry cluster and so on. We just try to help them connect, share ideas, and discuss and reflect about the progress. We also work with some state initiatives like Digital University, creating content on artificial intelligence, open source technology, and so on, that we share so that they can use later in some classes or courses. And we work with the ecosystem also in diversity and inclusion initiatives like Sisters in STEM, where we invite girls from a high school to consider engineering and science careers as a good option for them. No? We would like to see more women in the engineering careers. Other programs like Technovation, where we partner with other companies to foster high school girls also to develop applications that have an impact in our community and so on. So this is programs that help us provide value to our community, but also help us develop new talent that later can join us or other company. This is some numbers. In 10 programs, we have more than 100 per year. Majority is on Bachelor, but we do have a Master and PhD interns. They stay from 6 months to 1 year, or sometimes multi-year periods. Around 50 of our engineers teach at the universities. That's a way also where we take this knowledge to the university ecosystem. We have 20 ambassadors, meaning one of our engineers represents one university and is connected with that university. And in that way, we're more efficient providing support or bringing some initiatives from the university to us. We help and we partner with research and universities, research centers and universities on specialization programs like this one that we call PATS. More than 500 engineers have gotten a specialization. And this is a program of 3 to 6 months that specializes in something that we believe is going to be attractive for not only for Intel, but for other companies in the region, and has turned out to be very good. What the universities tell us is that after the specialization program, almost everyone has a good job opportunity to do what they would like to do. We support master degree programs. I mean, some of our engineers teach, but also some of our engineers take that program. More than 100 of our engineers have been taking the program, set up the innovation labs. As I mentioned, Sisters in STEM, in the last 3 years or so, more than 500 girls have attended this program. Technovation, more than 200. And we have, prior to the pandemic, frequent visits to our campus. Normally, every year, more than 5,000 college, university or high school students visited the campus. And the idea is to inspire them to continue in their career, whatever their career was. So with that, I will stop and I will introduce my colleagues that they will talk about the specific projects and developments that we are doing to impact, on one hand, quantum computing, and the other hand, IP for the future processors. But I leave you with a phrase from one of our founders, Robert Noyce: don't be encumbered by past history, go off and do something wonderful. Basically, this is a call to kind of be inspired, to do some new developments, change what is currently available, improve what we can improve, and do wonderful things. I think we have the passion and we have the talent to do it. We need to aspire to that, do it, and demonstrate that we can do it. So with that, let me introduce Esdras, that will talk about this integrated cryogenic control for quantum computing. So Esdras is a SoC design engineer, is member of our GDC Intel Labs silicon prototyping, where he led and developed the full chip integration of the first integrated cryogenic spin qubit controller in 22 nanometers technology. Before joining Intel, he worked at Freescale Semiconductors as a senior analog IC designer and technical lead, where he designed analog and mixed mode, high speed and low jitter circuits for communication processors. Since 2005, he has been a part-time professor of analog integrated circuits design at ITESO University. With that, welcome, Esdras.
Thank you, Jesus. Good afternoon, everybody. I'm really happy to be here and to have the chance to share with you this amazing project we had the chance to develop across different Intel Lab geos. So, as probably you heard during the last year, probably you heard a lot about quantum computing and especially about what is called quantum supremacy. So in this talk, I will try to cover a little bit and explain why people is so interested in this field. So let me start with what are the qubits. So as you know, in the digital world, we have the bits, which can represent 0 or 1. And in the same way, in the quantum world, in the quantum computing world, we have what is called the quantum bits, or qubits, as they are called. So the qubits are essentially quantum mechanical device that can exhibit multiple states simultaneously. That is called superposition. And then that's allowed to scale exponentially the total number of states when they are coupled. That is called entanglement. So in order to explain these two basic qubit properties, let me take a very raw example as when you have a coin. As you know, when you have a coin, you have a head or tail. But when you flip the coin is passing across head and tail at the same time. And that is exactly what happened with a qubit. When it's having superposition, the qubit can be 0 and 1 at the same time. So the second property, which is called entanglement, is essentially when you have 2 or more qubits. And basically, we can see them again, taking as a reference the coin example. When you flip 2 coins, at the same time, both coins are being head and tail at the same time. So in these ways, they can, in the case of the qubits, they cannot be treated as an independent state, and they form what is called a super state. As you can see here, basically what is happening is that the total number of states available using 2 or more qubits rise exponentially. And those two properties are essentially the basics of the quantum computing. So let me go to the next slide and explain now which are the potential applications for quantum computing. So the potential applications are so many. So, and it depends of the number of qubits used. For example, if we take a look at where is currently the state of the art, we are talking about more or less 50 entangled qubits, and this allows to get much more states than any possible supercomputer as we have now. So, but in order to get some application as cryptography, we will need not only 50 or 100, we will need even millions in order to provide essentially the error correction needed to truly obtain quantum computing, quantum computer. So what is quantum supremacy? Quantum supremacy is basically the goal of demonstrating that a programmable quantum device can solve a problem that a classical computer practically not. And this is the main goal of behind a quantum processor, essentially to be able to solve problems in a very fast way, which the current state of the art of computers is not able to solve right now. Okay, so let me show you how it looks right now, two of the most widely used qubits. So basically, the qubit we have here at the left is what is called a transmon or superconducting qubit, which essentially you can think about it as a nonlinear LC circuit which emulates an artificial atom. So this qubit is essentially the solid state device which has an operation frequency of 4 to 8 gigahertz and needs about minus 60 dBm of power in order to work or operate correctly. On the other hand, at the right side, we have which is called the spin qubit, which is essentially and truly a device where we can control the spin of the electrons trapped in a quantum dots. And in this case, this device is able to work in a frequency range from 12 to 20 gigahertz and needing a power operation of about minus 30 dBms. So these two devices right now are the most promising devices among the different qubits that are available. And it's worth to mention that perhaps this one, the transmon, is the one that has been more widely used across different research centers and companies. So having defined how the qubits looks, let's take a look at how the quantum computing looks today. So essentially, the quantum computing right now makes use of a workstation in order to run the algorithms and needs these huge racks where are generated the different AC signals, plus another huge rack where we have all the DC signals needed in order to bias correctly the qubits and the different, and provide the behavior that is expected. One of the main drawbacks that we are facing right now in the quantum computing is that in order to drive a qubit, we need to list at least 2 lines in order to drive every qubit we have here. And in addition, since in order to preserve the quantum effects and the qubit needs to be isolated from external world. So, and that is why they need to be located inside a very specific fridge, which needs to operate at very low temperatures, very close to the absolute zero, so around 20 millikelvins. So what we have here at the right is essentially what is called a dilution fridge, where the qubits are located and basically going down in temperature from room temperature and then going down up to get the 20 millikelvins degrees, which is the temperature where the qubits are truly operated. Okay, as you can see, one of the main drawbacks here is the fact that we need at least 2 lines per every qubit we need to handle. That imposes a very severe constraint when you are trying to get truly a scalable computer and not using just a few qubits, especially if you are trying to build some applications for cryptography. Okay, let me talk about what is the current state of the art in terms of the quantum computer and what is the proposed architecture proposed by Intel. Essentially, the state of the art basically makes use of all the control electronics located at room temperature. That means 300 Kelvin. And then sending at least 1 or 2 wires in order to control each one of the qubits that we have located inside the dilution fridge. So as we saw in the previous slide, so that imposes several restrictions, very tight restrictions when you are trying to escalate and get a really or a truly quantum computer. So in order to tackle this problem, the Intel proposal basically is to take all this control electronic and move inside the fridge to operate at the 3 kelvins and put these control electronics as close as possible to the qubits themselves. So in this way, we are able to reduce those all bulky instruments and those cables and put them together in order to better control the qubits, reducing the huge space needed, also gaining a lot of improvement in terms of the performance. Also, in order to reduce the total amounts of cables needed to handle or to drive the qubits, it is also proposed to use frequency multiplexing in order to use a single line and be able to drive several qubits at the same time. So those are the two main features of the the integrated proposed controller by Intel, which is called Horridge, and that we are proposing to pave the way for the quantum computing. So let me go to the next slide. So let's take a look now in a deeper way how the Horridge circuit architecture looks. So one of the restrictions that we have here is basically the signals that we need to generate. They need to be very stable in terms of frequency. And there is a parameter called fidelity, which basically is a measure about the quality of your signals generated. So in order to get and be able to fulfill the very stringent specification for this circuit, it is needed to make all the generation of all the signals in the digital domain. So basically in Horridge, we have essentially 4 transmitters where every transmitter has 32 channels. Basically, we have here 32 numerical oscillators with correction, and then we have a polar modulator which produces the quadrature signals, and we have also some circuitry in order to produce quadrature correction. So these signals essentially are the outputs from all the digital part and are sent basically to the analog. In the analog, we have 2 digital to analog converters in order to take these outputs and then generate the quadrature analog signals. We provide some filtering here, and we have some voltage gain amplifiers in order to produce the adequate gain for the total path. So those signals are then sent to a radio frequency stage here, which is pretty much what is used in a typical radio frequency system with the multipliers or the mixers. And then we generate 2 kinds of signals. The first signals we generate here are essentially aimed to drive the transmons qubits that we saw in a few slides ago. And the second set of signals we generate here are essentially to drive the spin qubits. So the solution we are proposing essentially are able to drive the 2 qubits, the 2 types of qubits that have been used so far widely. So here below, we can take a look about how it looks, the schematics for each one of the analog portion. For example, for the DAC, as you can appreciate, this is a kind of current steering DAC here. So we have a GMC filter for provide the low pass filtering that we need. These are the mixers in order to provide the quadratures and so on. So as I already mentioned, at the end, we provide 2 type of signals from the 2 to 15 gigahertz output range for the transmon, and from the 15 to 20 gigahertz for the spin qubits. So let's take a look at how it looks the chip when it's already integrated. So as you can see here, we have the 4 transmitters that I was talking about. We have the transmitter 0 here, the 1, the 2, and the 3. So all of them are essentially the same one, they're just replicated another 3 times in the chip. So here you can appreciate which is the part belonging to the digital and the part belonging to the analog. So the four transmitters are connected to the external world across a serial to parallel interface. And this chip was designed using the Intel 22 nanometers FFL technology. So as I mentioned, it supports from 2 to 20 gigahertz microwave outputs in order to be able to handle transmons and spin qubits. And the total power consumption is around 330 milliamps milliwatts for the digital part and about 1.7 milliwatts per qubit for the analog. The signal to noise ratio is large in that 44 dBs for a 25 megahertz bandwidth. So this is how it looks, the chips integrated. And now let me talk about how this chip was integrated into the dilution fridge. So here we only have one transmitter from the total chip, so where you can appreciate the bumps in order to be connected to the external world. So the total chip, as we saw in the previous slide, is a 4 by 4 millimeters. So each transmitter is roughly about 2 millimeters by 2 millimeters. So when it's packaged, the total package size is around 19 millimeters. So this is a picture of the chip already packaged here. And this package is then put inside a PCB plus thermalization, which is this, what we have here. And that plate is basically the one that is located inside of the dilution fridge, and is located in the part that operates between the 3 and 4 Kelvin degrees. So again, the qubits are located at the lowest temperature, so at 20 millikelvin, and our circuitry is currently operated at 3 Kelvin. So let me talk about a few of the measurement results. As you can imagine, so since we are using frequency multiplexing in order to reduce the total number of lines and be able to drive multiple qubits at the same time, it is very important that we be able to minimize the coupling between the different qubits. So it is possible to show that one way to minimize the coupling among the different qubits being driven by the controller on a single line is basically if you change the profile used, the modulation profile to drive the qubits. So one of the requirements that this kind of controller needs to fulfill is essentially to be an arbitrary generator waveform. So in order to be able to generate the different profiles and waveforms associated with the control of each of the individual qubits. So just to put an example here, you can see that with the controller, we are able to generate a cosine pulse, a rise cosine pulse, a rectangular pulse, a triangular pulse, or even a Gaussian pulse. So, and with that, we are able to set the different carriers to control each one of the qubits in a different channels. So with this, basically, we are enabled to be able to drive up to 128 qubits using this integrated solution. So one of the tests that needs to be done in terms of the qubits control is basically to rise at or to develop a test which is essentially to control the spin of the electron and then be able to switch among the different states. So that means between the 0 and the 1 states. So in order to generate that test, it is usually conducted a test which plot what is called the Rabi frequency, which is basically to apply a pulse and then with certain duration and then apply twice that pulse, that time duration and so on in order to get completely the flip of the qubit. So when you plot that versus the time, you can see that the probability across the change of states between 0 and 1 is produced. And that is one of the measurements that basically proves that you are able to control truly the qubits. So this work was presented at the International Solid State Circuits Conference this year in February. So if you want to learn more, please, if you can download that paper where much more information is explained and reported there. Or also you can check each one of these links, which are public, and there is much more information about Horwich and all the work developed behind this project. So thank you very much. It has been a pleasure and hope to have the chance to talk to you in the future. Thank you, Jesus.
Thank you, Esdras. And now let's move to the Next part by Jorge. Jorge Hermosillo is the site representative for the custom logic engineering team in GDC. He has been at Intel more than 15 years as a technical leader in post-silicon validation, research scientist as part of Intel Labs, a platform application engineer for Xeon products, and more recently as a manager of the network acceleration design and validation team in Guadalajara. Thank you, Jorge.
Thank you, Jesus. Thank you. It's a pleasure to be here sharing with you what we do in Guadalajara. So let me move to this slide. Usually, we identify Intel as a company that is working for CPUs, for laptops, and for PCs. But it's really more in this new era. It's really more a data-centric company. And as Jesus was saying, the Guadalajara Design Center is mainly focused on this part of the company, on the data center, on the data platforms. On this new era, Intel is attacking the market through three different vectors. The first one is, as you can see here on the left-hand side, is we know there's a ton of information right now being generated, content being generated for all kinds of devices, and we need to move that data quickly from the point that it is generated to the point that is consumed or where it is processed. So we are focused on moving the data as fast as possible, and you can see there are different platforms that Intel is offering to do that. At the same time, we need to have a way to store this data for later use. So Intel is committed also to provide the platforms to store as much as we are generating right now. And in this regard, the Optane platform with the 3D cross-point memory is a platform that Intel is using both for solid state drives and for persistent memory. And I will talk a little bit more about this. And of course, the jewel in the crown here in Intel is the processor. So we need to process everything. All this data that is coming needs to be processed and delivered to the point where it's going to be consumed, and to the point that is going to be stored. So we have the Xeon processors in conjunction with the FPGAs and accelerators like Nirvana for artificial intelligence to do this processing. So this is the general picture of the company. In Guadalajara, in the silicon design teams, we are focusing on two of these vectors, on the moving the data, storing the data, and working in three different technologies. The first one is on the 5G edge infrastructure. Intel is now a leading provider for the platforms that are going to be deployed for 5G around the world. So we are working on providing silicon IP to these platforms that can allow to get the deployments and get the 5G technology as a reality. We are working also on a network interface cards acceleration. So the network interface cards are something that has been in the market for a long time. These are the regular Ethernet cards that we know. But with the amount of data and the amount of processing that we need to do right now, these cards are getting smarter and smarter. So we are putting more and more IP to do the acceleration of the processing in the network card versus doing it in software in the processor. And as I mentioned, we use the Optane platform, the Optane technology for memory to store data. So let me go to the next one. I want to show you some details on the different teams that are working on these technologies in Guadalajara. In this one, I'm showing some details about the Optane memory using the Optane platform using the 3D cross-point memory. So when we look at how this thing really looks like in a platform, it looks like a regular DDR DIMM, as you can see in the top. So it is connected to the same DDR bus, but it instead of coming with standard DDR memories, it comes with solid state memories based on 3D cross-point, but it also requires a microcontroller that in conjunction with the CPU. We will have a CPU from Intel that understands how to talk to this memory. It provides a platform to create a level of memory that is between the storage as we know it in the hard disk and also the storage that we know in the DDR. It sits in the middle, providing more density than DDR, a little bit less speed than DDR, but it acts as a cache for the information that we have in the either the solid state drives or the hard drives. So the same concept that we use in the CPU as a cache for the accesses to memory, this obtained memory is working as a cache for the storage and improving the efficiency considerably. The microcontroller that you see in the middle at the bottom is the one that has the intelligence to talk to the CPU and to talk to this solid state memory. And in Guadalajara, we have a team that is working on the design and the pre-silicon validation for this block. The next one. Here I'm showing some evolution of the network cards, on the Ethernet cards, and they have been around for a while. But as I have mentioned, with every new generation, we are adding more and more intelligence to these cards, basically offloading the processing from the CPU that traditionally is done in software to do it in hardware. Mainly for two reasons. One is to accelerate, of course, make it closer to where the data is getting to the platform, and the other one is to release cycles from the CPU, because the CPUs right now are being used. One of the main usages for them is the cloud, and the cloud needs to have the CPU available for the customers. We don't want to use the CPU for this overhead in terms of processing what is happening on the network. So we want to have them available for the customers of the cloud. One of the key technologies that is moving to the network cards is technology known as RDMA, either in the two variants that we have in the industry, as iWarp and also as Rocky. In this case, Rocky V2. So there's a team in Guadalajara that is working on these blocks for RDMA and acceleration in the network interface card, and both for logic design and for pre-silicon validation, and even in the microarchitecture case. Moving to the next one. QAT is a technology that is coming in the Xeon processor from Intel. This is also an accelerator. It's also for network packet processing. This is not close to the network card because it's closer to the processing that is happening on the CPU, mainly for three areas. It's for crypto, as let's say, as the regular VPNs that we use, that everything is encrypted. This is an accelerator for that kind of application. It's also for the PKE, the public key encryption, and the storage, and also in compression and decompression, and trying to reduce the amount of data that we're transmitting through the network in, of course, in a lossless way. The Guadalajara team also has been participating in delivering IP for this QAT technology, mainly in the compression side, and adding new standard algorithms that are being developed by industry into this technology that has been around for a while in the Xeon processors. And the last case that I wanted to show you is in the developing silicon for the FlexRun concept. FlexRun concept is related to the software-defined network. Is the concept of the deployments that we currently have for 4G and for 5G. And this is something that goes into the base stations when we are processing the wireless signal from the mobile devices and transforming that into packets that can be sent to the infrastructure network. The team that is working on this is currently working on algorithms for forward error correction for these two technologies. Because that is right now is not something that we can do in software in the CPU at the rates that we currently have. So we need to deliver that as part of a companion accelerator to the CPU. So the main objective of this is to deliver silicon, to deliver chips that can be used in the base stations and also in the IT infrastructure for the wireless providers, so they can have all the processing that they need for their deployments. So as a summary, the Guadalajara Development Center, we have a pre-silicon team, as Jesus mentioned in his initial presentation. Going into some detail on the level of activities that we do, we participate in several disciplines. I already mentioned microarchitecture, logic design, and pre-silicon validation, but it's not only on the logic side. We are participating also in the analog side with analog circuit design, mixed signal partition design, and physical design for all these IPs. Currently, we have some of these IPs in real silicon being validated in the lab, and but the team that is working on the design is right now working on the future generations, things that we are expecting to see in the CPUs and smart cards in the 2 or 3 years from now. So with that, I turn it back to you, Jesus.
Thank you, Jorge. So with that, I think we're open for questions.
Okay, thank you very much, Jesus, Esdras, and Jorge, for the very interesting talk. So now we are open for questions. I have here one question from Mais Inflado. So the question is, which material is used for interconnects in quantum computers?
Right now, you can think as a regular cable, as this is the current state of the art.
Okay. So waiting for other questions. I have also one that how many people you have in Guadalajara working on IC design?
So we have a Jorge's team that overall under his organization is close to 100, but we have other groups that develop models, what we call virtual platforms, models for FPGA emulation and so on. That might be another 50. So I might say total in the range of 150. Yeah. Jorge, you want to add anything?
No,
Nice.
no, that's correct.
Yeah.
Thanks,
Nice
Jesus.
number. Yeah. So now a question by Carlos Cortez that is now in Tokyo. So very late there, but so Jesus mentioned about university ambassadors and in this interconnect world, what are your thoughts of the connections and the possibility to work with international universities?
I think it's a very good question, and right now, something that the pandemic has shown us is that we can explore new ways to connect through this digital technology. I mean, example in Guadalajara, right now, due to the pandemic, 85% of us are working from home. So we have been focused on connecting to universities locally because we are used to that face-to-face and physical contact and so on. But now I think the floor is open for other connections with other universities using this type of technology. So the answer is yes. I mean, certainly we're open for more collaborations beyond the current universities that are in Mexico.
Yeah, it would be great to have more cooperation with universities in Latin America, no?
Yes,
So,
I completely agree.
This is always in bad moments like this COVID-19, we can find a new ways or new path, you know, to do new collaborations and so on. And as we have now today this possibility to have your great talk directly from Guadalajara to even to Carlos that is now in Tokyo, you know. He has also another question. Can you tell us a bit more of the research activities in the Intel in Guadalajara Design Center?
Sure. Edras, do you want to answer that?
Oh, okay. Yep. Well, as Jesus mentioned, there are other activities related, for example, physical design, there are artificial intelligence. So there is an SOC group. So another group which basically works with drones. So they made the algorithms to that. So another group which is in charge of basically provide all the technology in order to implement the hardware are the projects that are being developing. So there are the knowledge among the different groups is huge. So there are many disciplines being being put together on different projects. So I think the slide that you mentioned, Jesus, or you shown, is the best to describe exactly what is being done in terms of the research at Intel Labs Mexico.
Yeah, and sometimes that changes. I mean, that is the current focus area. In the past, maybe 5 years ago, it was a different one. But as Esdra mentioned, is artificial intelligence, recognition of sound, prototyping, autonomous systems, not only cars but drones and others. No? So that is the current focus areas for Intel in Guadalajara.
So a question here by Juan Pablo Martinez Brito that works at Hightech at Porto Alegre. Are you hired at Intel Guadalajara? What type of engineer profile are you looking for? Is the standard working language Spanish?
Yes, so the answer is yes. We're hiring not as intense as in last year due to the current conditions, but from time to time there is new requisitions in different areas. So mainly background on electronics or computer design and all the mix that exists on mechatronics and so on. But kind of electronics and computer design is the base. Bachelor, Masters, and PhD. So we look at the three profiles. Basically, it is English, the common language for communication, because we enter a lot of meetings and so on. Certainly, if you are at the site, at the cafeteria, or talking to locals, Spanish. But collaborating with the engineers across the world, English, and several meetings are also held in English. So yes, I mean, if you're interested, go to www.intel.com/jobs/Mexico, and you find their description of what we're looking for, and that changes from month to month.
Okay, thank you very much. So I don't see any more questions here for the moment. So so we have also a relation with Intel Costa Rica, I suppose.
Yes, we partner a lot with Intel Costa Rica in different aspects. No, I mean some of the functions that they lead on finance, human resources, corporate services, and so on, help us at the side, no, from that leadership in Costa Rica. They also have engineering teams, and we partner with them in several aspects. For example, there is some segment of products that they own a piece of the development, we own other piece of the development, so we partner as we come together as the overall product life cycle to take that prototype into a product. So yes, it's a frequent conversation, frequent collaboration, and great partnership with Intel Costa Rica.
So as probably you know, we have now in Brazil the most crazy and worst government ever, no? So and this could be expected because anybody that they took a look in his profile as a candidate, we cannot expect a good government. Anyway, now they don't see and they don't have a strategy for the development of the country, you know, in the technology industry and so on. And they are willing to close CEDA, that is the only foundry in South America, no? And also with a design center. So maybe Intel could consider to buy CEDA and to expand activities to south of Brazil.
I will let know my partners about that possibility. Certainly, if you send information, I can forward it to my partners to evaluate that. But I do believe that the best investment a country can do is on education, then certainly research, technology development. That is the basis for a community and societal advance. So I hope that in our countries, in general, in Latin America, we do invest more on education. I think it is important, and it is deserved by the great talent that it is here, that we invest more in them.
Our hope is that this government will not stay forever. No? So, okay, so I don't have more questions now for the moment. So thank you all for this nice talk. And I hope that we'll be able to meet in person in the near future. No, so we don't know when now, but thank you very much. And,
thank you.
I hope to see you soon, and also maybe to have another virtual meeting in the near future also.
Sure. And likewise, I mean, we will talk about how we can bring some of that great talent and knowledge from you guys into this campus. That will be great. So yeah, let's keep in touch and see how we can collaborate more to develop more talent in our region.
Okay, thank you very much. So
thank you.
Thank you.
So bye-bye, everybody. Have a nice end of afternoon and beginning of night. See you soon.